Our dear listeners out there, yeah, thank you. This is the simplifier again. Uh, we are cut out for simplifying science, make it look as simple as it is. Today in chemistry, we will continue from our last video. Now, last video, I explained, especially the students who asked us to explain, to lay more emphasis on the equilibrium constant. And thank you very much for the appreciation that we got from you. Now, I can say, yes, you understand because you sent me a message and you said, yes, wow, it's now better understood. That is our aim. That is the objective that the simplifier has. And thank God that we are meeting those objectives. Now, today we're going to continue with the last aspect of endothermic and exothermic reaction. Remember, these are under chemical changes, or let's simply put, energy changes. Energy changes. So here, endothermic and exothermic. First, I'll start by explaining these terminologies. What's an endothermic reaction? Endothermic reaction. And what's an exothermic reaction? Yeah, in your biology sense, remember, look at this word, endo and exo. Yeah, when you were looking at biology under classification, remember that it was classified, we have the vertebrates, the invertebrates. That is, by the way, I just want to use a little of biology. You know, they are all linked. Biology, physics, and chemistry are all linked. And that is why the sciences, they are just too easy. They are very easy, and that is our aim. So if we look at this, if I link this to biology, we have endo and we have exo. Now remember, endo has to do with what? Inside. While exo has to do with what? Outside. Remember that organisms that have their skeletons outside their body, we have this word assigned to them, exoskeleton. Yeah, things like your crabs and the rest of them. You know, a student once asked me this question, what is the tongue of a snail called? Yeah, and I'm asking you, my viewers out there, what is the tongue of a snail called? You say to me, it's not possible. No textbook has given that. Trust me, you will get that today. Look at this word. Don't forget the radula. This is the name given to the tongue of a snail. Yeah, it got a tongue, the radula. Now that's, by the way, radula. At least you've learned something today. Now look at this. So exo, we have outside. Endo, we have this meaning inside. So what's an endothermic reaction? This is the reaction during which heat is absorbed from the surroundings. Now, if I carry out an experiment, an endothermic reaction, something will be noticed. You will notice that the environment where this reaction is carried out will become very cold. Become very cold. Now, that means heat has been absorbed from the surrounding. Now, but if I carry out that reaction and the outer vessel becomes very hot, it shows that the reaction is exothermic. Because an exothermic reaction is a reaction during which heat is given off or liberated to the environment. Now, last class, I gave you an example. I said, for example, if I have barium hydroxide reacting with ammonium chloride, now this reaction will yield a compound that will cause the external environment to become very cool. And I told you if you carry out this reaction with, let's say, a beaker, and just below the beaker, you have water settling. Upon reaction, when products are formed, you will understand this will become very, very cold. It will turn to ice even. That shows you the amount of heat that has been absorbed from the surroundings. But look at the Haber process, where I have nitrogen combining with hydrogen to give me ammonia. Now this reaction, I told you the enthalpy change for this reaction is negative. It shows us that what? That this reaction is exothermic. Any reaction that is carried out and you have delta H as negative, it shows you that that reaction is exothermic. That means heat will be liberated into the environment. So if I carry out this experiment, even if I do this in a test tube, if you touch the body of the test tube, it will become very, very hot. It shows you that large amount of heat has been liberated to the environment. Now, I want to give you a better understanding of endothermic and exothermic processes. Look at this, an energy profile diagram. I will draw two main energy profile diagrams, one for endothermic and one for exothermic. Pardon me, I'm a very good artist, so I'm going to draw it very well. So I have this. I have something like this. And I have the second one. And I have something like this. This is my A plus B. Yeah, remember the reactant. And this my C plus D, the product. This is my A plus B also, my reactant. This is my C plus D, the product. Now we're going to label this. Let's make this nice. The peak of this diagram is called the activated complex. We have the activated complex. Now from this activated complex to where your reactant is, remember I call this activation energy. Yeah, the enemy of our reaction. I call this the activation energy. Now look at this. This is still my activated complex. This is my activated complex. From this point to the reactant, oh, a very small activation energy. That is where the reactant is. This is my reactant, this is my product. The distance or the difference noticed between the reactant and the product is called my enthalpy change. So I'll just note that here. Delta H is called the enthalpy change. And take note, this is the formula for delta H. That is the heat content of the product minus the heat content of the reactant. The same thing will happen here. My delta H for the reaction will be the heat content of the product minus the heat content of the reactant. Now, take note. Remember, if this is 1, this is 2, this is 3, it increases. This is my energy change, kilojoules per mole. Now, if I subtract reactant from product, now, which one is higher? Yeah, you got that right. The product is higher than the reactant. And that means if I subtract the reactant from the product here, I will get a positive value. So my delta H here is going to be positive. That's because product is higher than reactant. If I do the same thing here, my delta H, which one is higher? Yeah, the reactant. That means if I make product minus reactant, I'm going to get a negative value. This will be positive, and this will be negative. So if you're asked to draw the energy profile diagram for each of endothermic and exothermic, this one with a delta H value to be positive is the endothermic reaction. Why this one with a delta H value as negative is my exothermic reaction. Now remember, this is not the only reaction or formula you have for your enthalpy change. It can connect with so many things. Your enthalpy change is related to your free energy change, your Gibbs free energy change. Your enthalpy change is related to the entropy change, the degree of disorderliness or randomness of a chemical system. We have that. So I have delta G is delta H minus T delta S. This is a formula relating free energy with enthalpy, temperature change in Kelvin, and entropy change. We also have this, delta G is minus RT ln K. This is my free energy change. This is my molar gas constant, the temperature in Kelvin, and of course, this is a stoichiometric value. Your ln K, if you don't want to use this, you can actually convert it to a log form. This is 2.303 log. This is the meaning of ln K. Ln K, ln is 2.303 log. That is ln. So if you want to convert this to logarithmic form, you can actually do that. So this is endothermic and this is exothermic. Now you can actually use that to determine which is an endothermic or exothermic reaction, or which reaction occurs at equilibrium. Please take note that whenever your delta G value, your free energy change is 0, this means that reaction is at equilibrium. The reaction is at equilibrium. That is when delta G is 0. Now, when delta S is positive, That means the entropy change here is pretty high. Now remember, there was a particular question that was asked. Look at water in 3 different states. I have water in liquid form, I have water in gaseous form, and I have water in solid form. 3 different states for water. Yeah, this is ice. This is your water vapor. And of course, this is your liquid water. Now, if I have this water in liquid form, going to water in gaseous form, and going to water in, or let's take it the reverse. I have water in solid form, going to water in liquid form, then going to water in gaseous form. Entropy is increasing because gases have the higher level of entropy, the higher level of disorderliness observed in a chemical system. So if I have a gas and I have a solid, a gas will have a larger entropy as compared to your solid. Remember, entropy, degree of disorderliness. How disorderly can the particle be? I trust you got that. Now, with this simple analogy, I trust you understand what endothermic reactions are and what exothermic reactions are. Now, before I end my video today, remember, carbon dioxide also can exist in solid form. Yeah. Solid carbon dioxide is called dry ice. That is solid carbon dioxide. It's referred to as dry ice. Now, as we progress in other videos, I will give you other names for compounds. Compounds that you might not naturally see in some of your books, but which are asked in exams. This is one of them. Your dry ice is solid carbon dioxide. Remember, carbon dioxide exists in gaseous form also. Take note. Now, I'll leave you with this. I have the solid, I have the liquid, and I have the gas. To convert from solid to liquid, that is what? Melting. To convert from liquid to solid, that is freezing. To convert from liquid to gas, that is evaporation. To convert from gas to liquid, that is condensation. And that is how rain is formed. To convert from gas to solid and solid to gas. Look at this. Textbooks will tell you, yes, solid to gas, this is sublimation. But it is erroneous to say from gas to solid is sublimation. That is an error. Please, I put it to you now. The simplifier is telling you from your gas to solid is not sublimation, but rather deposition. So I believe you've noted this. As we continue in our other videos, we'll look at carbon and its compounds, we pick up some inorganic compounds, and there will be a time where we'll pick up organic compounds. Remember, I said to you some time ago that if you're interested for us to pick up a particular topic, to lay emphasis on those topics, or to create an insight about those topics, you are very free. Send it to us as a comment, a review, or a feedback. Remember, visit our page on Instagram and on Facebook, The Simplifier One. And of course, please don't forget, click that subscribe button so that you keep these videos going. On YouTube, remember, The Simplifier One. Thank you.